Okay, so thanks for having me, I guess, at this wonderful workshop. So I'm giving 2 lectures on Vark-Scholze, and somehow since Vark-Scholze is rather large for 2 lectures, I'm just doing 2 very specific parts of it. One of them is the spectral action. So today I want to do this, and then tomorrow I want to talk about charts. Okay, so this is some very maybe non-obvious selection of topics, but I think this is what makes sense for me to talk about. And so if you're new to this, so I think Karyani's Bun-G talk is also an excellent. Okay, sorry, I'm misspelling it. Better, right? Yeah. Okay. Yeah. So Karyani's Bun-G talk is, I think, a very kind of reasonable overview of what is in Vark-Scholze, and of course also the introduction to Vark-Scholze itself. So I've written some kind of notes, which I guess will become available soon. But so let me start by just giving some recap. Okay, so some recap, or maybe just some notation I will need. Okay, so there'll be some higher algebra later that I'll pretend I understand, and you can pretend with me, okay? And then yeah, there's I think an adult in the room who does understand this, so I think we should be fine. Okay, so we have F. F is a local field. With the residue field FQ. And G over F connects to the reductive. So K is F cube bar, and perf is perfectoid spaces over F cube bar. Okay, that's what I called K. And then I have G over F connected reductive. And then I have Bun G sort of on perf. This V stack that I think we've seen before, so it's a stack of. So there, I think my right hand is, the notability settings here are slightly different than my own.
I apologize, the podium is too short for you.
That's also true, yeah. So okay, Bun G on perf is a stack of G bundles. Stack of G bundles on the Vark-Fontaine curve. So I want to recap a little bit what Mingjia did at the end yesterday, which is Hecke operators. And to get Hecke operators, we first of all, we need this very important diagram. So we have this global Hecke stack over Bun G with this map H1. And I'll recall in a moment what these things are. Bun G times div 1. And then there's also a local Hecke stack, which is a curly H. Okay, so what are these things? So if I fix some R plus, right? So here we have sort of G bundles E, And here we have these triples. Okay, so I'm over div1, so I need to have a Cartier divisor D, and then I have my E, guess my E1 and my E2 and my alpha from this modification. And H1 just forgets everything except for E1. And here I'm just remembering D and E2. And here on the local Hecke stack, I'm remembering D and somehow like alpha restricted to the Fark-Fontaine curve over RR plus completed around D. Okay, so D and then alpha restricted to D inside X Fark-Fontaine hats. That's one way to write it. So I just look at this formal completion, which is what these people usually call be the RAM of D, and then.
Do you want to label if the other arrows should be H2?
Yeah, so I do want to call this H2. This map here doesn't have an arrow, the map from global Hecke stack to local Hecke stack, and usually you just omit it from the sort of, even the pullback there doesn't have a name. Okay? So I'm trying to get my notes to scroll down. Okay. And so, okay, so basically the idea is like, or the slogan is, so sheaves on this local Hecke stack they give Fourier-Mukai kernels. They give kernels. Fourier-Mukai kernels. On this global Hecke stack. Okay, so if I take a sheaf on this Hecke stack, local Hecke stack, I can pull it back to the global Hecke stack, and then I get a Fourier-Mukai functor like Ming-Jae wrote down yesterday. So pull back along H1, tensor with the kernel, and then push forward. So this is already interesting. So we need a source. So a source of sheaves. So a source of sheaves on Hecke G is geometric Hecke. So this was part of the preliminary, so I can just assume that everyone knows exactly what this is. But okay, in some sense it's not so bad. So yeah, maybe, I mean, I need to introduce a bit more notation before I can talk about it. Geometric Hecke, we'll see this in a moment. Okay, and then maybe one thing I'll sort of say is there's a kind of convolution product on Hecke, on the local Hecke stack. So there's a convolution diagram. So let me call this local Hecke tilde, and then so my subscripts G are going to start falling off at some point. Div1. So using this, you can kind of put a monoidal structure on sheaves on the local Hecke stack. So maybe I don't precisely want to tell you what is this Hecke, local Hecke stack tilde, but you can kind of guess, right? I mean, I have like pairs of E1, E2, and E3, and E4, and I want to sort of have an isomorphism between the middle part so that I can push forward, like compose the, so that I can compose the modifications. Okay, so this is all the geometry that I'll need today. Okay, so let's talk about sheaf theory. Okay, so I fix some L not equal to P. Okay, so P is the characteristic of my FQ. And I want lambda some sort of ZL and maybe a joint square root of Q algebra. So I need to sort of tell you what sheaf theory I'm using, and that's a complicated point. So I'm going to write, so for X, a small V stack. We will use, there's kind of two kind of sheaf theories I will use. So either I'll use D relative X lambda, or I'll use D etal X is D etal X lambda if L is nilpotent in lambda. L is nilpotent in lambda. Okay, so this D etal, this is not so scary. So this is almost 10-year-old theory at this point. So this is etal cohomology of diamonds. And there's also this paper by Lucas Mann, a 6-functor formalism for nuclear sheaves, where this is maybe the 6 functors they're written down in a slightly better way. Okay? So drel, so also see Lucas's. So here drel, okay, what is this? So one way of defining it is that there's something even scarier, which is Schulze has a kind of motivic overconvergent category. And okay, and I can tensor product this over the motivic category of a point. Okay, the point is just my my final object, so it's this spa diamond of FQ bar. And I can tensor product this with d lambda, I guess. D lambda. Okay, there's some kind of, right, there's a map from D of C motivic of a point to D lambda. It's more or less L-adic realization. Okay, and what does this tensor product mean? Okay, then, yeah, so now here we are, no. So this is C higher algebra. So yeah, I asked Dave if it was okay to just explain the D etal formalism, but somehow next week we're going to assume L is invertible on lambda. So I thought I should show you what's really happening. Okay, so this D rel is a little bit scary, but okay, at least it's some 6-functor formalism, and on a point it's just D lambda, okay? So maybe I should tell you, okay, what does D lambda mean? Okay, so here D lambda is the sort of derived category of lambda modules. Okay, so this is what my sheaf theory is. And okay, the reason I also want to use D etal is because many things are easier to explain with D etal than with D rel. And my strategy will be I'll explain everything with D etal, and then at the end, if I have time, I'll also explain what's really going on.
So there are going to be some relationship between these.
Right, okay, so there is a, so if L nilpotent in lambda, then there is indeed some fully faithful map to D etal. And we know what the essential image is. Okay, really there's some morphism of six functor formalisms, okay, and it's fully faithful, and we know what the essential image is. So let me just say explicit essential image. What else do I want to say? Yeah, so if you're happy to assume that L is nilpotent, you might as well pretend we're working with the étal. But I should sort of say remark is that, so the big difference between the two theories, as far as I'm concerned, is that d étal of a point and d étal of something like spud C, where C is an algebraic closure of F. Okay, so C is like F bar hat. And this is very false for D-rel. Okay, so it's not just a cosmetic thing, oh, we have to do something. Like there's a genuine difference, and this is what causes a lot of trouble for us later. Okay, so in my notes I have some theorem saying the six functor formalism D-rel is blah blah blah, has all these properties. Okay, so it's a Sheafy presentable six functor formalism, but I think I'll skip that. Okay, so the main object, so the main player is then, D of Bun G. Okay, so if I write D without any decorations, I'm being agnostic, right? Maybe I should write D question mark Bun G, where either of them could be happening. Okay, so now I can tell you what geometric Sataka is doing. So geometric Sataka gives me a good source of sheaves. Okay, so let G hat over lambda be the dual group. With this action of, right, so the dual group has an action of the V group of F, and then I have kind of the semi-direct product you might call this the L group of G. Sorry, that's, yeah. And what geometric Sataka tells you is, so the theorem is that, so first of all, there is a subcategory, Sataka G inside of D of the local Hecke stack. Stable on a convolution. Okay, so that means that this subcategory itself has a convolution product plus an exact symmetric monoidal equivalence. Symmetric monoidal equivalence. From rep of this G hat semi-direct product WF. And I guess I'll write here, okay, I have to tell you what kind of representations these are, okay. Sorry, is there a question?
You didn't write anything under the D, so I assume you mean either one.
Yeah, either one, yes. Okay, so yeah, that's, so in the étal setting, there's Fark-Schultz have something, and also in the D-rel setting, there's also Hansen and Mann have something. So I'm being agnostic about which one I'm using. And okay, so I have to tell you what kind of representations. So this is a kind of a funny group, right? It's like, so G hat is an algebraic group, and WF is a topological group. So this category is maybe slightly strange, But important to note that this is a sort of, this is like the 1-1 category. Okay, so there's no infinity stuff going on, a 1-1 category of representations on finite projective lambda modules such that, let me just say like this, G hat acts algebraically. And WF continuously. Yeah, so this is maybe a strange way of saying it, but yeah, I want sort of restricting to G hat, I want just an algebraic action, and restricting to WF, I want a continuous action. This is more or less what it is. Okay. So yeah, the reason for this, so maybe a remark is that, right, this local Hecke stack lives over div1, and that is why WF shows up. So you might be more used to geometric Sataka saying something like, I get representation of G hat, but div1 has some Galois information. So that's why I also need to put Galois information into the Sataka category. Okay? So in the étal setting, you can sort of base change along split C to div1 to get sort of Hecke, local Hecke stack G over C just being reps of G hat.
It's like set on the left.
Ah, yes, I want, okay, so, yeah, let me, so let me say there's D Hecke G over C, and inside of this there's a Sataka G over C, okay? So you can trivialize the Galois action when you pull back from split C, but this is in the Direl formalism, this is not.
Sorry to be annoying, but maybe that arrow isomorphism.
Sorry?
Slanted, no. Rep G hat should be mapping slantedly downwards.
Yes, yeah, sorry. Thanks.
Can I also ask a
Yes.
quick question? I may be missing something, but when G is trivial, with this complicator, you shouldn't see anything interesting, but then you still have reps of WF.
Right, so I guess when G is trivial, then Hecke G will just be div1, okay? So I guess I'm claiming that, and the Sataka category will just be sheaves on div1.
Oh, still you.
Yeah, and so sheaves on div1 is representation. So that's what my remark is trying to say. So this is a good way of putting it, yeah. So if G is trivial, then you still get sheaves on div1, and that's more or less where the Galois action comes from. Okay. Okay.
Like the ones coming from FUR.
I don't want to think in front of the board, yeah, but maybe, yeah. Okay, so this is what geometric Sataka is. So so now for K in Sataka G, so we get a functor TK from D Bun G to D Bun G times div1. Okay, so what am I going to do? Like I said, K is going to be the kernel, so I take F and I send it to H2 lower star of H1 upper star of F tensor with k. Okay, so maybe I'll scroll back up to my diagram. Here. So I take my k up here and I pull back, and then I get a Fourier-Mukai transform, sheaf here, pull back, tensor, push forward. Okay, so this is the basic ingredient of the spectral action. And so now, okay, now I have the branch between d étal and d rel, okay? Because I would like to be able to think of tk as just a functor from Bun G to itself. So in the étal setting, again, I can kind of, I have d étal Bun G, and it's just the same as d étal of Bun G over C. So what I can do is, this functor lands in d of Bun G times div 1, but I can just pull back to d Bun G of C. So get an endo functor tk from d of Bun G to d of Bun G C, which is again d of Bun G. Okay, and when I want to talk about the interaction between different Hecke operators, it's much more convenient to think of them as endo functors. Right, so I'm basically saying, yeah, this notation is slightly bad. So I'm just also going to call this tk, Hecke operator associated to k.
So here, Bun G C means like you base change the form C.
Yeah. So yeah, I can. That's a good point. So I can either take d Bun G times div 1 and base change along split C to div 1, but that's also just Bun G times split C along over the point. Okay, so now let me give you some results.
Once you tensor with K, you automatically get a shape whose support is proper.
Yes, right. They are the same, yes.
Well, you should probably explain the horizontal map of your diagram. It's derived from the thing you called TK before. It's slightly unclear.
Let me. Okay, so I have d Bun G, and I go to d Bun G times div 1. So let me call that tk. And then here I just have, let me call this delta star. So delta is just Bun G times split C down to Bun G times div 1. Morally, what I'm doing is I'm forgetting the Wave loop action. Right. And that's useful because then I can say things like this. I can say things like.
So do you want to draw a big slanted arrow to fill in the diagram?
Yes. Okay, so let me be slightly better and just call this SK. Okay, so now I can tell you how different Hecke operators interact. Okay, so I can now ask, for example, okay, they commute. That's hard. That's much harder to state if the target is not. Somehow then I have to have extra factors of div 1, et cetera, so I don't want to talk about this. And I sort of, even better, I have that, oh, no. So I have SK composed with SK prime. This is like S of K tensor with K prime. No, there's just one delta. Delta is just the map from, there's a map from split C to diff1, and yeah. So
I mean, are there many maps from C to the C to
no.
Maybe you should say that C is characteristic 0.
Yeah, so I mean, C is F bar hat.
We saw in Ming's talk yesterday that div1 is
Yeah.
split C modulo the V group.
Div1 is split C mod the V group. So that's the map that I'm taking. Yeah. So here this K tensor K prime is the sort of monoidal structure on this attacker category. So this is somehow saying that the Fourier-Mukai, that the kernels commute with convolution, which is a reasonable thing. Okay, and in particular, this will tell you that. So this will tell you that Sk is adjoint to Sk dual. It's even left and right adjoint to Sk dual, so it commutes with all limits and colimits. With limits and colimits. Yeah, and I want to say this proposition is just, I think in Fark-Schulze there's maybe less than one line talking about the proof of this. It's just some formal nonsense about convolution. So, but already you get a lot of structure out of this. So the next thing is that, so Sk preserves ULA objects, and it also preserves compact objects. So I'm not sure these have been discussed yet, whether or not, but for those of you who know what it is, let me also state this. And then finally, so Sk only depends on, so right, I have this Sataka G, which is the same as this rep of G hat semi-direct product WF. And I can kind of just forget the WF part. So it only depends on this composition. So this kind of makes sense, right? We're forgetting the V group action. So the V group action on the kernel should also not matter. But again, yeah, so it's crucial here that, sorry, let me just backtrack and put in these étal subscripts everywhere. Okay, so this is really only in the étal formalism that I can make such a nice statement. Okay, are there any questions so far?
The first 3 bullet points, right, this is a proposition about various properties.
Right, I'm just saying proposition.
Specialized to the étal case.
Yeah, I've done that. So I've only defined Sk in the étal setting. Yeah. Because only then this equivalence here is sort of étal only.
So this forgetting of the V group action in the Sataka category is only valid in that setting.
There's a way to do it in DREL that you refer to.
There's a way to do things in DREL, but it's just more painful. And there's also a way, Fark-Schulze do it using DLease, and that's also more painful. Yeah. So this is somehow the cleanest formulation of this. Any other questions? Also questions welcome from non-experts.
What does this last step mean?
Okay, so K lives in here, right? So I can, so let me just more precise, if you have K and K prime, and they become isomorphic under this forgetful map, then the Sk and Sk prime are isomorphic as functors.
So actually,
upgrade it to an action of all of rep G hat.
Yeah, you get an action of rep G hat. Yes. Okay, so this Galo action will be important in a moment, but for now it's not. For now it doesn't play a role. Okay, so now we can finally get to trying to state the spectral action. So I have this action of this rep G hat, and the spectral action sort of gives me more than that. Okay, so I have to recall this par G is a stack of L parameters. For G. Or if you like, sort of for G hat with its action of WF. And this has a tautological morphism. It maps to, I guess I'll just write spec lambda mod G hat. And so given a representation of G hat, I get some curly W in sort of a vector bundle on par G. So the idea of the spectral action is that I extend the action of rep G to an action of like vector bundles on par G, or even perfect complexes. Okay, so perf par G is the symmetric monoidal category of perfect complexes. Okay, so in particular it contains all the vector bundles. Sorry? That's not good. Okay, par G. Okay, and then the spectral action tells you that actually these perfect complexes act on Bun G. Okay, so the theorem that I want to state is that there is an action of perf par G on d et al Bun G. Such that, okay, so first of all, what does it mean for a category to act on a category? Okay, so again, I'll use my purple color, so C higher algebra. But the point is that perf is a symmetric monoidal category, so it's like an algebra. And d et al Bun G is like is just a stable category, so it's like a module. So I'm basically saying in the infinity categorical world, this algebra acts on this module. So that's a reasonable statement. So in particular, like for an object in perfect complexes, I should get an endofunctor of Bun G. Okay? So such that so here I'll sort of say a perfect complex P goes to an endofunctor, let me call it SP, such that for for one of these representations of G hat, if I look at S of this, okay, I guess I call it W, so S of curly W, okay, so that's, curly W is a perfect complex, so I can form this NO functor, and that is the same as sort of S of, let me just say F of normal W, where W, so where S normal W is this Hecke operator. Okay, so so above I had, for a representation of G hat semi-direct product of a group, I have this Hecke operator, but in fact I also have one for just W itself. Okay, so S curly W is SW. So what I want to sort of explain is what does this actually buy you? So how does this help?
So does that characterize the spectral action?
No. I think, so I will not have time for this, but there is a characterization of the spectral action, but then you have to keep track of these V-group actions as well. And that is, yeah. And maybe you'll see in a moment, I'll sort of tell you how the V-group action is used to get this, and then you'll see that, yeah, there is something more needed. Okay, so how does this help? Okay, so I said for every object, I get an endo functor, but because we're doing higher categories, also for every morphism, I get a natural transformation of endo functors. Okay? So in particular, and because it's an action of an algebra, the identity object, so O, should act as the identity on the other side. Right? That's an algebra action. One acts trivially in the higher categorical sense. So how does this help? So one consequence is that, so I can look at like endomorphisms. Sorry, and so experts will know I've omitted an assumption here on L. So I need to assume L is not terrible. So L, yeah.
L shouldn't divide the torsion order of the center.
Yes. So L should be co-prime to the order of the identity component of the center of G. Okay. So when L is 2, I'm excluding many groups. Yeah, SP to N and SO to N, etc. Okay, but somehow, I don't know. Most L's are fine. Okay, so consequence, so what was I saying? So endomorphisms on par G of O. So this is a ring. So the ring acts compatibly on every object in Bun G. On every. Right, so that's one particular consequence of this, what it means for an algebra to act. Okay, and okay, I say here the word ring, and you might be worried that okay, I'm taking endomorphisms in an infinity category, so maybe this is a derived ring, but it's not. That's also a theorem of Fark-Schulz. Okay, so This is a theorem. So Fark-Schulze basically say there's no higher endomorphisms of O on this stack. So if you want to think about it, like par G is like something mod G hat, and endomorphisms is just like G hat invariance of that. I mean, it's basically of like global functions upstairs. You take G hat invariance, and the higher endomorphism should be like the cohomology of G hat. Okay, but since we're in possibly characteristic L, this is a little bit scary. But in fact, Fark-Schulze proved that there is no such higher cohomology. Again, and that's also where this assumption on L is presumably necessary. Okay, so that's kind of nice. So for example, it acts on d étal of this Newton stratum Bun G1, which sits fully faithfully in d étal Bun G. And of course, we know what this is. This is just representation, the derived category of smooth representations on lambda modules of GQP. G of F, thank you.
Are you asserting it preserves this subcategory, or are you doing an extra step?
I'm saying it acts compatibly on every object, okay? So on a full subcategory, yes, yeah. So yeah, this is always a bit confusing. Am I taking, so I'm not moving the objects at all. I'm just saying it acts compatibly on all the objects. Yes.
The language of talked yesterday maps to the center of the function.
Yes, yeah, so that's one way of saying it. It maps to the center of the endomorphism ring of the identity functor, or the center. Okay, and so this ring has a name, this here. This is called Z spec G lambda. And it gives, and we also have a classical name for the ring of compatible endomorphisms of objects in this representations of the smooth thing, and that's the Bernstein center. So it gives a map from Z spec G lambda to the Bernstein center. Okay, so this is called the spectral Bernstein center. And this is called the usual Bernstein center. Yeah, I mean D, yes. Yes. So in Fark-Schulze, it's just called rep smooth, yes. Yeah, so yeah, it's a bit confusing. So I'm willing to add a D here, if that helps.
Would you mind?
Okay, I'll add a D.
But this causes no issue.
It's consistent with what Alexander
Ah.
But it still lands in the kind of usual Bernstein center. I mean, in other words, this D doesn't cause any issue.
Yeah, the Bernstein center is insensitive to derived versus not versus.
So yeah, a priori you get a map of animated or like derived rings, okay? And then you're saying, well, the thing on the left is just static, so it sits in degree 0, and the thing on the right maybe also sits, okay, so it also sits in degree 0, so there's no problem. Yeah.
What is the spectral Bernstein center?
Yeah, so I defined it as endomorphisms on par G of O. Okay, so it's just the ring of global sections on this stack.
For formal reasons, is this the categorical Bernstein center of modules on par G or something? Is it
Yes.
the endomorphisms of the unit?
I think it's also, yeah, I think it's also the categorical center if we take QCO rather than perf. Yes, so it is the categorical center.
Just to connect to yesterday's talk, this was what Shangshan notated as like the G hat invariance in Z1 WF hat. So
Right.
we did see the same ring yesterday.
Yeah, so let me add some, so this is also just H naught of part GO, and it's also just Z1 WF G hat invariance.
Oh, sorry, there's an O, like global section. No, sorry. Yeah, global section.
Yes. So yeah, it has these different descriptions.
9 different names.
Yes. I think spectral Bernstein center is a nice name. Okay, so in my remaining sort of, let's call it slightly less than 10 minutes.
Do we know some properties of this map?
No. Yeah, we know very little. I mean,
Well, not immediately out of the box.
right, I think in Fark-Schulze, so like, okay, so what they do is they prove that for GLN, it agrees with a similar kind of map constructed by Helm and Moss. But
In fact, for GLN, it's an isomorphism.
for GLN, it's an isomorphism, right? Which is,
Even in Italy.
yeah. I mean, you have to be slightly careful. Like, I think it's not known that the formation of this Bernstein center on the right commutes with base change in lambda. For the left-hand side, this does commute with, but like a priori, it could be really bad. So for torus, we know what it is by local class field theory, more or less. But like a priori, for some exceptional group, you could see like, I mean, this Bernstein center is like has like a product decomposition, and a priori, it could just. It could not, yeah, we don't have any idea that it's what it should be, okay? So I think, so there's a kind of, this is the H0 of a map of schemes, and this map of schemes is supposed to be a finite map, and we don't know that, okay? So this is, I think in general, this is still quite a mysterious map. So let me sort of. So maybe said differently, from the geometry, we don't have any way to control this map. The way we control this map is, you compare it to maps constructed in different ways, like allomorphic ways, and essentially global methods always have to come in to say anything about this map. Okay, but having the map, there's this really nice short paper, Helm, Korinchik, Moss, maybe 2 or 3 years ago, where they just say, okay, having this map itself already has consequences for the representation theory. Okay, so this corollary is not just this, or this consequence is not a small consequence, it's actually a big consequence.
Maybe it's valid to say that
compatible with
prove soft properties of this map.
Yes.
But like hard properties are hard.
Compatible with parabolic induction, that's known.
Like twisting.
Twisting, yeah. So there's some. Yeah, so Fark-Schulze has a section called the Bernstein Center, and there they sort of list what they can prove about this map. Again, like using soft methods. Okay, so I should really get to the construction. So how? So rather than trying to explain how the spectral action is constructed, I want to say how is this map constructed? So how is this action of the spectral Bernstein center constructed, of Z spec constructed? Okay, and I think maybe I'll have to take a little bit of time in my next lecture to. So basically, the idea is that. So I take some W in rep G hat semi-direct product WF, and I take maps 1 to W alpha and W to 1 beta in rep of G hat. Okay? And then, and associated to this, is an anamorphism of this curly W. Sorry, an anamorphism of O. On part G. right? So what am I going to do? Well, I get a morphism O to curly W, that's my alpha, and I have a morphism curly W to O, that's my beta. Sorry. I also have to choose some gamma in the V group. Okay? And now the nice thing about this W is that W has an action of the V group. So I can apply this gamma here. Okay, so what I'm doing here is that so basically there's a tautological phi from WF to the L group of G over par G, and I compose with LG to GLW to let WF act on W. Okay, so I can build endomorphisms of O using these kind of triples, so an alpha and a beta and a gamma. And this is a special case of what people call an excursion datum. So, so my W alpha beta gamma is an excursion datum. Okay, so now I just have to tell you what is the corresponding like endomorphism on the other side on Bun G. So here, basically what I'm going to do, so now take if I take F in d etal Bun G, then I have my TWF, which lives in d etal Bun G times diff 1. And actually, it turns out that this receives a natural functor from V group equivariant objects in Bun G. But I think it's actually an equivalence, right? So I can think of TWF as an element in Bun G with a V group action. So what I can do is I can look at, I have F, and then I can go to like, I have a map to SW of F coming from alpha, okay? And then, because SWF, I mean, it is just sort of TWF with the, so, okay, this is sort of TWF, and so now here there's an action of this gamma, and then I can apply beta, and I get back to F. Right, so I'm just saying that the spectral action is functorial in morphisms of representations, and the identity functor acts as, just sends F to F, so I get F alpha goes from F to SWF, and that is just TWF but now TWF remembers the Galois action. So I can apply this action of this element gamma, and then I can apply beta to go back to F. Okay? So this is sort of evidently functorial in F. So it doesn't, it gives you an endomorphism of F, which is, if I have a G, then I also have an endomorphism of G, and these things are compatible. So this here, I don't want to give it a name, but this is called an excursion operator. So excursion operator. Okay, and then the last thing I want to write down is that, so there's a theorem of, let me say it's essentially Vincent-Laforgue and Fark-Schulze, which is that these kind of excursion operators generate this anamorphism ring. So I haven't defined for you what an excursion operator is, but so anamorphism of par G of O is generated by excursion operators. And again, here I need this assumption on L does not divide the order of pi naught of CG. Okay, so first I show that I have certain anamorphisms of O, called these excursion anamorphisms, and associated to those, these act on D Bun G, and then I show that those exhaust all the anamorphisms. And so in general, I need to allow, there's somehow a finite set floating around that I've suppressed, and you need to allow somehow not just a representation of G hat, but a representation of G hat to some power, and yeah. Okay, I'll end here.